Hello, everyone, and welcome to my lab. Are you ready to have some fun? Yeah! Are you ready to learn? Yeah! Well, let's get started then. I have a sparker over here now. You know, in my lab, we have a lot of exciting experiments. I want you to pay close attention to what's going to happen. I want you to be on the lookout for loud noises, for color changes, for smoke, for fire. Try to think about what you see. Try to connect what you see with other things that you may have learned before. In my lab, we practice safety. I want everyone to notice that I have my goggles on to protect my eyes from potential splashes. I put my goggles on because it is the state law. I'm a law-abiding citizen. I also do it because it's good practice. I want everyone to know that I have a fire extinguisher right here, ready to be used, just in case something goes out of control. I'm not planning on anything going out of control, but it is a safety precaution. In fact, I'm going to set it aside right here where you can all see it, and I can reach for it as need be. Now I want to come back to the experiment that I did before, where I had the sparker, a plastic bottle with two nails stuck on the sides. They're not touching on the inside. They're separated by a distance of about ½ centimeter. At the bottom of the bottle, there's a small amount of a clear and colorless liquid we call alcohol, and there's a cork on the top. What I'm going to do is use the sparker and touch one of the nails to see if I can make the spark jump across the gap that separates the two nails. Okay, so are we ready for this? Here we go. That's an example of what we call an uncontrolled combustion reaction. The alcohol vapor inside the bottle burned and ejected the cork way up there. That's an experiment that simulates what goes on inside the internal combustion engine, where you have a piston, you have spark plugs, and you have fuel that burns. And that we want the burn to be smooth there, not uncontrolled combustion as we have seen over here. I'm going to do another set of experiments now where I take a liquid. This liquid is called bromine. It is in a sealed small vial. Bromine is element number 35 in the periodic table. You know, this is the 35th anniversary of my special lecture. And so, yes. And so, yeah, thank you. Thank you. And bromine is a volatile liquid. I'm going to take this sealed glass ampule and drop it into this cylinder that is full of air. That's what I'm going to do. So I'm going to drop it so it breaks. Here we go. Did it break? Yep. Okay, put the cover on because I want you to know all colored gases are poisonous. If you ever see a colored gas, you run away from it because all colored gases are poisonous. Now, we're not running away from this one because it's closed at the top. Bromine liquid changes into a vapor, and the vapor is the same color as the bromine, a slightly lighter color. And we see from this experiment that the mixing of the bromine gas with air, which is a mixture of nitrogen and oxygen, takes place very slowly. This process we call diffusion. Diffusion is a very slow process. We'll keep an eye on this and see what the level of bromine vapor will be as time goes by. What I'd like to ask you to do now is to look at this long tube that I have over here. It has been evacuated. There's no air in it. No air in it whatsoever. And it is sealed. What I'm going to do, I have a side arm. And inside this side arm, there is another small vial of bromine. I'm going to break this. I want you to pay close attention and see what happens as this reaction takes place. Here we go. Did you see that? There's no diffusion here because the tube was evacuated and the bromine vapor filled the tube immediately, unlike what's happening in the mixture over here. I want to do a set of experiments with the beakers that I have in front of me here. I have 2 rows of beakers. The first row has 1, 2, 3, 4, 5, 6, 7 beakers, and so does the second row. And the beakers have in them a clear, both rows of beakers have in them clear and colorless liquids. And I want to see what happens when we mix the contents of the beakers in the back row with what's in the front row. All right? So here we go. I start by adding this one, and I want to count. 1, 2, 3, 4, 5. All right, let's see what we can do with the second one, all right? All right, here we go. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Very good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very good. It goes to 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Pretty close, right? You're changing the cadence on me now. Maybe I'm changing it too. All right, let's do one more. 1, 2, 3, 4, 5, 6, 7, 8. Pretty good, right? Pretty good. All right. This is, did you like that? The next experiment that I want to do, whoops, I've forgotten what the next experiment is now. I got so excited and carried out with that experiment over here. So actually, I happen to have a copy of the book that I wrote here. This book is called Chemical Demonstrations. You see that right here, right? And it's written Bassam Shakhashiri. You see that down here? It's my book. I wrote this book here, all right? So bear with me as I open the book and read the instructions for the next experiment. Will you permit me to do that? Okay. Oh, you're very kind. Thank you. Thank you. Oops. This is not an ordinary book. This is a real hot book. Actually, it's not a book at all. It's just the book covers. On the inside, there are 2 batteries, a light bulb, and a flint that I soaked with lighter fluid when you weren't looking. You all know about the fire triangle. It takes 3 things to have a fire. Something that burns, oxygen, usually from the air, and then you need heat or a source of ignition, right? What I haven't told you yet, but I'm going to tell you right now, is right down here, right down there, there's a small red button. Can you see the red button? Yeah. All right. When I push the red button, chemical energy that's stored in the batteries changes into light energy, and the light bulb comes on. But this light bulb, like all other light bulbs, is not 100% efficient. It gives off light energy and heat. And the heat ignites the lighter fluid. So, you ready to see this? I move this away from my face, right? And I push the button. And there is the fire. Now, you tell me what happens when I close the book. What happened when I close the book? Well, I heard at least 2 different answers, all right? You're like the students in my class. Some of you are like the students in my class. You give a correct answer, but not to the question that I asked. The question that I asked was, what happened when I closed the book? What happened? The fire went out. Why did the fire go out? Because there was no more oxygen, right? All right? So, I opened the book now. Is there oxygen or not? Yes. But there's no fire. How come? No heat. So what should I do? Push the button away from my face, right? We push the button, and there it is, okay? We teach about the fire triangle so people learn how to put out fires, not to start fires, all right? All right, thank you. By the way, I'd like you to take one more look at the bromine and how it's diffusing. The bromine gas is diffusing in air. Take another look at that because I'm going to move it out of the way. I'm going to do more experiments with bromine. This experiment that I'm going to do with bromine is in this device that I have over here. This is a sealed tube. I have some bromine liquid right down here at the bottom. And above it, you can see the color of the bromine vapor. It's pretty close to the color of the bromine. It's not quite as dark. And then if you follow me all the way up here, you can see that there is a bulb that has some bromine in it. And what I want to do is cool down that bromine down here. So I'm going to use some liquid nitrogen, put that like so, and jack it up. And I want you to watch for changes in the color of the bromine vapor in the tube. All right? So a little more is good, right? Not always, but again, in this case, it's good. And take a close look at what's happening to the color of the bromine vapor, because the whole apparatus is sealed. And liquid bromine was changing into vapor, and vapor bromine was changing into a liquid. But now that I have cooled down the liquid bromine here, it's frozen. The melting point of bromine is -7 degrees Celsius. And if you look carefully, you can see a change in the intensity of the color up here. But way up here in the bulb, there is some liquid bromine. This liquid bromine is changing, some of it is changing into gaseous bromine. When a liquid evaporates, that's a cooling process. You know that. Evaporation is a cooling process. And what's going to happen here is that in a short period of time, the top surface of the liquid bromine here is going to get so cold it will freeze. But there's a lot of liquid bromine below it, and we'll see, well, we'll wait and see what happens, right? So we just have to be patient about this. We try to help the process a little bit by adding more liquid nitrogen to cool it down, because that will speed up the process. And if you look, let me jack it up some more. If you look near the top, I'm beginning to see some thin film of solid bromine. You see it? You see it? Huh? You see it? Now, the liquid bromine has a vapor pressure, and let's see what happens there. It broke that thin layer of frozen bromine, and then we get another layer of frozen bromine, and this process continues for a long, long time. Now, I want to do an experiment whereby I take some gas from in a burner. I'm going to turn the burner on, turn the gas on, and then light the burner. And you see the flame, of course. Do you see the flame? Maybe we'll see it better in the dark, right? Let's turn the lights down, all right? The lights go down, and more, some more. Okay, here we go. Now what color is the flame? Mostly blue, and now? Green. And now? Green. How about if I do it together like this? Isn't that pretty, right? All right, with the lights back up, please. With the lights back up. These spray bottles have in them different chemicals. The red one is lithium chloride dissolved in some alcohol, and this one is boron dissolved in some alcohol. And when the lithium hits the hot flame, the electrons in it get excited to a higher energy level, but when they drop back to where they started from, they give off light energy, and we see this beautiful characteristic color. It's like a fingerprint for lithium. And for boron, it's this way. And all the elements in the periodic table have their own characteristic emission colors when they are heated in flames. And I just thought that was a pretty neat experiment to look at again, right? To do it this way, right? There we go. At this time, I would like you to welcome my very long collaborator and friend, Dr. Rodney Schreiner. Rod? Hi, Rod.
Hello, Bassam.
What do you have for us today?
Well, I have a tube made of copper, and I'm going to use it with these two pieces of metal, two small pieces of metal. I'll set them down here. They're exactly the same size, and they even look pretty much the same. But they're not exactly the same. What I'm going to do is I'm going to drop each one of them through this tube. So I'll drop it through. Ouch, that was loud. And it falls all the way through the tube, right down to the floor, very fast, just the way you would expect it if I let it go without sending it through the tube. So, very fast. Now let's try the other piece of metal. I'll again drop it through. Now, where is it? Where is it? Ah, there. Where is it? There it is. Let me see. Can I catch it? Oh, yeah. That's amazing, isn't it? I think that's really quite spectacular. I suppose you want to know why it works that way. These two pieces of metal are not the same, as you would probably have guessed already. And in fact, one of them is a magnet and the other one is not. And I can show you which one is the magnet. Let's see, where are my keys? Here are my keys. If I put my keys on that one, that's the one I dropped in first. It's not a magnet. The one I dropped in second, that's a magnet. And in fact, it's a very strong magnet. But let go. It's a very strong magnet. But that still doesn't explain all of what you saw, because you all know probably that copper, such as this tube is made of, does not attract a magnet. It's not that this is magnetic alone. It is that this magnet is falling through a piece of metal that conducts electricity. Whenever a magnet moves past something that conducts electricity, electricity will flow in that piece of metal. So when I drop it, the magnet into this tube, electricity starts flowing around the tube. Where is it? Someplace. Okay, it's making its way down. The electric current is flowing around, and whenever an electric current flows, it generates, there we are, it generates a magnet. And the magnet that's generated by the current opposes this magnet, and that holds it inside the tube for much longer time. So that's why it's working.
Very interesting, Rod. Any other experiments?
As a matter of fact, I have a few more.
All right.
You know, I said that when you get a magnet you can get magnets that oppose each other, and you probably already know that magnets have two poles, the north pole and the south pole, and when you have a north pole approaching a south pole, the two magnets attract each other like that. But if you turn one of the magnets over, then you will have a south pole coming toward a south pole, and they do not attract. In fact, they repel each other, and I find it's hard to get them to stick together. I can show you that even more clearly by putting these two magnets onto this glass stand. There's one magnet, and I'll put the other one on in the opposite direction. And they repel each other, so they do not come together. And in fact, I can put a few more on here. Let's drop another one on. And let's drop another one on. Oops. That was the wrong way. I'll try that again. Turn it over. Drop it on. And there we have magnetic levitation. Now, also I told you with this tube that a flowing current generates a magnet. And that is exactly what makes a motor, an electric motor, work. And you can actually build your own electric motor with some very simple equipment. All you need is some wire, a plastic cup, some rubber bands, and some paper clips. What you do is first, of course, you're going to need some magnets. Let me get some magnets here. You put one magnet on the outside of the cup, the other one on the inside. They'll stick together, so they hold. Then you put rubber bands around the cup, and you unbend a paper clip into a straight loop so that it's going to hold the part of the motor that moves. And then you set that under the rubber band. You put one on each side. I have one already put together so you can see what this looks like. Here it is. It's got two paper clips. Now the last thing you need to do is to make the part that the electricity is going to flow through. That's through a wire that you make into a coil. The easiest way to do this, I have found, is to take a thin piece of wire and wrap it around a 9-volt battery. I've already done that. And so it looks something like this, a piece of wire wrapped around a 9-volt battery, and it has two ends sticking out on opposite sides. So what I have made is a little ring that will swing on these paper clips. See if I can get them in there, like that. And then it moves very easily. Now all I need now is to pass electric current through that ring. It'll generate a magnet, and these magnets down here will interact with it and cause it to move. So let's stop it, and I'll get current from another battery in a holder with some clips on it. And I'll attach one to one side, one clip on one side, one clip on the other side. And it wants to go. You saw it start going. It just needs a little push, I think. There we go. And away it goes. Thank you. Thank you.
Rod, do you suppose sometime soon we can have on our website instructions for people to construct this simple motor?
Absolutely.
Sometime soon. You go to our
yes.
website, sci-fun.org, and you'll find instructions not only for this experiment, but for many other experiments. Thank you very much, Rodney. Really appreciate it. Thank you. So, I have a clear and colorless liquid that has in it some household ammonia and some silver nitrate. I'm going to put that in there. That's the first liquid. And the second liquid is a sugar solution, except it's not sucrose, it is dextrose. So I add the dextrose in there. And what I want to do is get that rubber stopper on again. And of course, we have to mix the chemicals together. You can tell already that there is what? A color change. A color change is an indication that a chemical reaction is taking place. Do you see what I see? I see myself back here. And so what we've done here is make ourselves a silver mirror. So the reaction between the dextrose and the silver nitrate in the ammonia solution resulted in the deposition of a thin film of metallic silver. In fact, this is how silver mirrors can be made. And thank you. Now, ladies and gentlemen, you've been a wonderful audience. I really want to thank you for coming to the 35th anniversary of this very special program. I wish you the best in whatever you do, and remember, no matter what you do, that science is fun. Thank you very much. Thank you, everyone. Thank you. Thank you very much. Thank you.